Hi everybody. This is lesson 3.3. It's our last lesson for unit number 3. And similar to the last unit where we did ordinary simple annuities, this is finding the payment and the value of n, or the number of payment periods, for an ordinary general annuity. So just like in lesson 3.1, the first lesson we did, the formulas are the same as unit 2. What you'll notice is that equivalent rate of interest term, P, is present in each one of these in place of the periodic interest rate again. So these annuities are important, especially finding payment for something like a mortgage. Okay, so a lot of you, if you buy a house or you have a house, for your mortgage, a lot of times you'll pay monthly or you'll pay bi-weekly, but your interest isn't compounded bi-weekly or monthly. A lot of times it's compounded semi-annually. Okay, so this type of calculation would be what the banks would use when they're trying to find your payment value, okay, on something like your mortgage. So just remember, in ordinary general annuity, like I said, the interest, compounding frequency, and the number of payment periods per year, those two values are not the same. For finding payment, again, these formulas look very similar to what we did in Unit 2, and that's because they're exactly the same formula with one exception. Everywhere that the periodic interest rate was I is replaced by this equivalent interest rate, P. Okay, so these two formulas that are provided, one is if you know the future value, and one is if you know the present value. So present value questions are typically ones where you have loans. Future value questions are questions where you're trying to accumulate to a certain value of money. Okay, so you're trying to get to a certain amount of money within a time period. So remember, I put this little sidebar here. P is the equivalent rate of interest, and what it does is it translates your interest rate, assuming it was done, let's say, quarterly, and translating it so it's equivalent to whatever your payment periods are. If your payment periods are semi-annually and they're different, it translates that to give you an equivalent rate of interest you can use in these formulas. The reason it does that is, remember, the other item you have to calculate is this variable C, which is a ratio. It's the ratio of the number of interest compounding periods divided by the number of payment periods, both per year. Okay? So again, just like in lesson 3.1, this is the two extra steps that you have to do before you can actually use these formulas. So I'm going to do some examples, whether you know the future value and whether you know the present value, just so you can kind of see some of these differences. So let's start with finding payment if you know the future value. So what sum of money must be deposited at the end of every 3 months into a savings account paying 6% per annum compounded monthly to accumulate to $25,000 in 10 years? So starting with this question, a couple things to notice. It's asking for a sum of money. Okay, that signals that you need to find the payment. And it's saying that it's accumulating to $25,000. That's how you know that that is the future value, $25,000. The other items to note is money is deposited every 3 months, which is quarterly, and it's at the end of the month. But interest is compounded monthly. So payments at the end of the month make it an ordinary annuity. And since the compounding and payment frequencies are different, this is an ordinary general annuity. So let's start by writing out our formula. Okay, so we know we're finding the payment, and that's equal to the future value, and again I use the subscript G for a general annuity, times that equivalent interest rate P, divided by 1 plus the equivalent interest rate P to the exponent n minus 1. So a couple items we know the future value is given in the question of 25,000. We know the nominal interest rate is 6%, which is 6 divided by 100, removing the percentage sign, or 0.06. Our number of interest compounding periods, M, okay, is 12 because interest is compounded monthly. Okay, so our periodic interest rate, I, is equal to J divided by M, or 0.06 divided by 12, which gives you 0.005. All right? Our next item that we need to know is we need to know C. So C is your number of interest periods divided by your number of payment periods, both per year. So interest is monthly. Let's give this a value of 12. Okay. And our payment periods, okay, is quarterly, which is 4. So that gives us a value of C of 3. So now we can calculate the equivalent rate of interest, P. And that's 1 plus your periodic interest rate to the exponent C minus 1. In this case, it's 1 plus 0.005 to the exponent 3 minus 1. And if you calculate that out, you get a value of P of 0.01508. The last item you need is total number of payment periods, N. And we're paying for 10 years. Okay, and we're paying quarterly every 3 months. So 10 times 4 gives us a value of 40. Substituting all of these values in, we get our payment is equal to our future value, 25,000, times our equivalent rate of interest, 0.01508, divided by 1 plus our equivalent interest rate, 0.01508, to the exponent 40 minus 1. So I'm going to show you a few steps just solving the numerator and the denominator, just so that you can see what the numbers should be if you're working through this problem. So if you do the numerator, okay, you get 377, and the denominator, you should get 0.819746, okay? And if you calculate that out, your payment is equal to $459.90. You'll notice, again, due to rounding, that the answer's a few cents different than the solution that I provided. So looking at another example, if you want to have a $5,000 balance in your savings account in 3 years, how much must you deposit at the end of each month if interest is 4% compounded quarterly? Okay, so again, you're trying to have a certain balance in your savings account in 3 years, so you know it's a future value, and it's asking how much for you to deposit. So it's asking you for the payment. So knowing it's that you have a future value and you're trying to find a payment, you start with the formula. Payment is equal to your future value times your equivalent rate of interest divided by 1 plus that equivalent rate of interest to the exponent n minus 1. So now, again, on the right-hand side, your future value, you know, is $5,000. It's how much you want in that account. Your nominal rate of interest is 4%, which is 4 divided by 100, removing the percentage sign, or 0.04. Your number of interest compounding periods, interest is compounded quarterly, so M is 4. So your periodic interest rate, I, is J divided by M, or 0.04 divided by 4, which gives you 0.01. So now we have to calculate our ratio, C. And again, that's our number of interest periods divided by our number of payment periods. So interest is compounded quarterly, so it's equal to 4. And our payments are at the end of each month. Okay, so our payments is 12. That gives us a repeating decimal, 0.33. Okay? Using that, we can now solve for our equivalent rate of interest, P, and that's 1 plus our periodic interest rate to the exponent C minus 1, which is 1 plus 0.01 to the exponent 0.33, again, it's a repeating decimal, minus 1. And that gives us an equivalent interest rate of 0.003322. Okay? You'll notice for a lot of these where your number of payment periods is far larger than your number of interest periods, you're going to end up with a very small number for your equivalent rate of interest. Again, because it's trying to translate that quarterly payments versus monthly interest rates so that it gives you an equivalent value to use in the formula. Our last item is N, our total number of payment periods. So our account is 3 years. And again, we're depositing at the end of each month. So we're depositing 12 times per year, which gives us a value of N of 36. So now we substitute those values into our formula, and our payment is equal to our future value, $5,000, times our equivalent rate of interest, 0.003322, divided by 1 plus 0.003322 to the exponent 36, or number of payment periods, minus 1. And if you calculate the numerator and denominator out, you should get 16.61 divided by 0.1268. Okay? And that gives you a payment of $130.98. Right? Now let's look at, again, finding payment, but assuming that you know the present value. Okay? Janice applied for a mortgage for $190,000 for their first house. The mortgage will be for 25 years with interest at 4.9% per annum compounded semi-annually. What is the size of the monthly payment made at the end of each month? So again, you'll see it's usually a loan for present value. In this case, it's a mortgage, which is a loan. So you know that you know the present value, and it's asking for the size of the monthly payment. Okay, so you know you're finding payment and you know you have present value. So you start with that formula. Payment, and that's equal to the present value. Again, I use the subscript G for a general annuity, times your equivalent rate of interest, divided by 1 minus 1 divided by 1 plus an equivalent interest rate to the exponent N. So just like in the future value question, just stating what you know your present value is $190,000. You know your nominal interest rate is 4.9%, which is 4.9 divided by 100, removing the percentage sign, or 0.049. Your number of interest compounding periods, interest is compounded semi-annually, so that value is 2. So your periodic interest rate, I, is equal to J divided by M, or 0.049 divided by 2. Okay? And that gives you 0.0245. Okay? Next, we have to calculate the ratio C. Okay, and that's the number of interest periods divided by the number of payment periods. So again, interest is compounded semi-annually, but you're paying monthly. So your payments are 12. And this gives you a repeating decimal, 0.166 repeating. So now you can calculate your equivalent interest rate, P, and that's 1 plus the periodic interest rate, the exponent, the exponent C minus 1, which in this case is 1 plus 0.0245 to the exponent 0.166, it's a repeating decimal, minus 1. And that gives you an interest rate of 0.004042. Again, you'll notice that because we had far more payments than we did have interest periods, that you end up with a very small equivalent interest rate. The last item is the number of payments, N. Okay, so she has her mortgage for 25 years, and she's making monthly payments. So that's 12, and that gives you a value of N of 300. So again, substituting all of these values in, your payment is equal to 190,000 times 0.004042 divided by 1 minus 1 divided by, and then it's 1 plus 0.004042, and that's the exponent 300. So again, I'm going to show you this in steps. Okay, so the numerator, if you calculate it out, you should get $767.98 divided by 0.70185. Again, those numbers are slightly rounded. And if you place that in your calculator, you'll get a payment of $1,094.22. All right? So let's look at a second example. Ted bought a new car valued at $19,500. He paid $4,000 down and financed the remaining amount over 5 years at 8% per annum compounded semi-annually. How much must, I wrote Derek here. I should say Ted. How much must Ted pay at the end of each month? So there's one additional tweak in here, but before I talk about that, okay, he bought a new car for $19,500. Okay, that means he's got to pay that car back. So that's the present value. And the second item you see in this question is how much must he pay at the end of each month? Okay, so that's how you know you're looking for payment. So if we start with the formula, payment is equal to our present value times our equivalent rate of interest divided by 1 minus 1 divided by 1 plus our equivalent rate of interest to the exponent n. Okay, so what do we know in this question? One thing we know, all right, is we know our present value, but it's a little different here. Our present value is actually what he paid for the car minus how much he paid down on it, right? Because he doesn't have a loan for that total amount. He paid $4,000 right when he bought the car. So his present value is actually $15,500, right? That's the remaining balance he has to pay off over the next 5 years. So his nominal rate of interest is 8%, which is 8 divided by 100, removing the percentage sign, or 0.08. His number of interest compounding periods is compounded semi-annually. So that means that M is 2. So his periodic interest rate, I, is J divided by M, or 0.08 divided by 2, which gives you 0.04. So our next item, okay, following the same trends we've been doing the last 3 questions, we have to find C. The number of interest periods divided by the number of payment periods, which in this case, for interest, it's semi-annually, which is 2, but his payments are monthly, okay, which is 12. And again, just like the last example, that gives you 0.166 as a repeating decimal. So now we can calculate P, and that's 1 plus our periodic interest rate to the exponent C minus 1. In this case, it's 1 plus 0.04 to the exponent 0.166. Again, that's a repeating decimal, minus 1. And that gives us an equivalent interest rate of 0.006558. Last item we need is our total number of payment periods, N. And that's equal, he's paying for 5 years, and he's paying at the end of each month. So 5 years times 12 payments a year gives us a value of 60. So substituting that into our equation here, okay, our payment is equal to 15,500 times our equivalent rate of interest, 0.006558, divided by 1 minus 1 divided by, okay, 1 plus our equivalent rate of interest, 0.006558, to the exponent 60. So again, if you calculate these out, the payment will be, in the numerator, 101.649 divided by 0.32443. Okay, I'm giving you these intermediate numbers just if you're doing this problem yourself to see if you're getting the same numbers or if your calculator, you're not entering them correctly into your calculator. So if you calculate that out, you get $313.32. Okay, so that would be his monthly payments. So now let's look at finding N, the total number of payment periods. Okay, so again, these formulas look familiar. They're the same formulas from the second unit with the exception of everywhere and had the periodic interest rate. We've changed it for this equivalent rate of interest, P. And again, I've kept this little sidebar on the right here, just so you can remember it, okay? So the formulas, just like payment, depend on whether you know the future value or the present value. And again, the way the questions are worded, if you're trying to accumulate value, especially accumulating in a savings account, then the value you know is usually the future value. If you have a mortgage or car payment or a loan that you're paying off, that is usually giving you the present value. Okay, so let's look at a few examples. So let's look at some examples for finding n. Again, I'm going to do 2 examples of finding n and knowing the future value, and then we'll do 2 examples knowing the present value. So our first question, how many months are required for $125 deposited at the end of each month at 11% per annum interest compounded quarterly to grow to $15,000? So what you'll notice here is it says to grow to $15,000. That tells you it's a future value. And by asking for how many months, you know that you're trying to find n, okay, the number of periods. All right? So knowing that, just like we have in the past, okay, we start with our formula. Okay, so we know the future value, meaning that our value of n is equal to the ln, and that's the future value. Again, I put the G here to represent an ordinary general annuity, times our equivalent interest rate, P, divided by our payment. And that is plus 1. And remember, this is plus 1. That's all in the brackets, and that's all to be multiplied, or to have the ln taken out. Okay, so the plus 1 is not outside of the bracket that includes ln. Okay, so we'll see what that means when I go through the full formula. And that's divided by the ln of 1 plus that equivalent interest rate. So the variables that we know here, very simply, are future value, given in the question, 15,000. Our payments were also given in the question, okay, 125. Now, our nominal interest rate, 11%, which is equal to 11 divided by 100, removing the percentage sign, which is 0.11. Now, our number of interest compounding periods is compounded quarterly, so m is 4. So that means our periodic interest rate I, which is j divided by m, is 0.11 divided by 4, or 0.0275. Okay? So knowing those, okay, our next steps, just like we did in the past, we have to calculate our ratio C. And that's our number of interest periods divided by our number of payment periods. So our interest periods is quarterly, but our payments were at the end of each month. Okay, so that means monthly. So it's 4 divided by 12, which gives you 0.33, and that is a repeating decimal. Okay. Now we can calculate our equivalent interest rate P, and that's 1 plus our periodic interest rate to the exponent C minus 1. And that's equal to 1 plus 0.0275 to the exponent 0.33, again a repeating decimal, minus 1. And if we calculate that out, we get a value for P of 0.009084. Okay? That's everything we need here because we don't need to calculate n because that's what we're trying to find in our formula. So substituting all those values in, n is equal to the ln, and in the numerator we've got our future value, 15,000, times our periodic interest rate, 0.009084, not periodic, sorry, our equivalent interest rate, divided by your payments, which is 125, and that's plus 1, n bracket, divided by the ln of 1 plus the equivalent interest rate, 0.009084. Okay? So if we take that a step further and simplify both, all right, we should get that n is equal to the ln, and the numerator is 2.09008, and the denominator is the ln of 1.009084. Okay? If you put those in your calculator, you should get 0.7372 for the numerator and 0.009043 for the denominator. Okay, I'm showing you these steps so that you can follow along using your calculator. Try and find maybe one of those mistakes that I did see some of you make in the Unit 2 test. Okay, so if you do that, you get a value of n, which is 81.52, or in other words, 82 months. Okay, the reason we know it's months, all right, is because our payment period has already been provided in months. So it's 82 payment periods, which because our payments are monthly, it means 82 months. So let's look at a second example. How many payments will it take for your bank account to grow to $6,000 if you deposit $450 at the end of each month and interest is 9% per annum compounded semi-annually? Again, keywords here, grow to $6,000. Okay, so we know that that's your future value you want to obtain. And the second piece is asking, okay, so how many payments? Not what the payment is, how many payments? That means you're trying to find the value of n. So we start with our formula. N is equal to the ln of the future value times that equivalent interest rate P divided by the payment plus 1, all in brackets, divided by the ln of 1 plus the equivalent interest rate P. So again, what values do we know? The future value, we know, it's 6,000. Our payments was also given as $450. Our nominal interest rate is 9%, which is 9 divided by 100, removing the percentage sign, which is 0.09. In this case, our number of interest compounding periods, M. Okay, interest is compounded semi-annually, so M is 2. So we can calculate our periodic interest rate, I, which is J divided by M, which is 0.09 divided by 2, or 0.045. Next, just like we have in the past, we have to calculate C, which is the number of interest payments per year divided by the number of payment periods per year. Interest is semi-annually, so that's 2. And you're depositing $450 at the end of each month, meaning it's monthly, so your number of payment periods per year is 12. And if you calculate that out, you get 0.166 as a repeating decimal. So now we can calculate your equivalent interest rate, P. And that's equal to 1 plus the periodic interest rate, I, to the exponent C minus 1, which is equal to 1 plus 0.045, and that's to the exponent 0.166, again, a repeating decimal, minus 1. And if you calculate that out, you get an equivalent interest rate of 0.007363. Okay? Knowing all this information, again, we now plug it into the formula. So N is equal to the ln of 6,000 times your equivalent interest rate P, 0.007363, divided by your payments, 450, that's one calculation, plus 1, end bracket, divided by the ln of 1 plus your equivalent interest rate, 0.007363. So if you continue with these calculations, you should get the N is equal to ln of 1.09817, or something close depending on what your rounding is, divided by the ln of 1.007363. And if you do the ln on your calculator for both, the numerator should be 0.093648 divided by 0.007336. Okay, I did notice on your test a lot of you showed all of these steps, which is great. If you run out of time in a test and you don't show every step where you're doing individual numbers, that's okay. You know, I still want you to show, I need you to show everything on this right-hand side, but if you skip a step, within the calculation, it's okay. It does make it harder to do part marks. This way really allowed me to see everywhere that you made a mistake. All right, so it's up to you, okay? But know that you do need to show this information here, okay? So if you finish this calculation, you get a value of n of 12.77, which rounds to about 13 payments, okay? So our next example now is looking at finding n if you know the present value. Again, it's just a different formula to use when solving for n. A business valued at $96,000 is bought for a down payment of 25% and payments of $4,000 at the end of every quarter. If interest is 9% per annum compounded monthly, how many quarterly payments need to be made? Okay, so we know that they bought the business for $96,000 and only paid 25% down. All right. So knowing that, you know that they have a loan because they have to pay that money back. So you know the present value. Second item is asking for how many quarterly payments. So if it's asking for how many payments, that means you're trying to solve for the term n. So if it's n and the present value, we start with our formula. N is equal to the ln. And this is the present value formula, not the future value. So 1 minus the present value. Again, I use the subscript G here just to denote that it's an ordinary general annuity, times your equivalent interest rate P divided by your payment. And that's divided by the negative ln of 1 plus your equivalent interest rate P. So a couple things to note here. Right off the bat, you know that your payments are $4,000. Your present value is a little different though, right? They paid 25% of that business value down. So that means the remaining 75% is the amount that they have to pay on their loan. That's the present value of their loan, right? Because since they paid off that 25%, it's not included in their loan. So your present value then is $96,000 minus 25%, okay, or 0.25 times 96,000, right? Because you're removing 25% of that cost. If you do that, you get that your present value is 96,000 minus 24,000, or $72,000. Okay? You have to remember when you read this question, when somebody does do a down payment, remember that that's not the present value of their loan anymore because they've paid it. All right? Next item to calculate, we know J, the nominal interest rate, is 9%, which is 9 divided by 100, removing the percentage sign, or 0.09. Our number of interest compounding periods, it's compounded monthly, so that means M is 12. So your periodic interest rate, I, is equal to J divided by M, or 0.09 divided by 12, which is 0.0075. The next item we've got to calculate, a ratio C. It's the number of interest payments divided by the number of payment periods. Sorry, interest periods divided by payment periods. Interest is monthly, and your payments are every quarter. So that means your number of payment periods per year is 4. So you get a value of C of 3. So the last item to calculate, your equivalent interest rate P. And that's 1 plus your periodic interest rate to the exponent C minus 1. In this case, it's 1 plus 0.0075 to the exponent 3 minus 1. And that gives you a value for P of 0.02267. So you can see this value is much larger, right? There's less zeros after the decimal, and that's because your exponent here is a whole number. It's 3. It's a lot larger, okay? In the past, they were, 0.16 with a repeating decimal, 0.33 with a repeating decimal. So you'll notice that this number is quite a bit larger. So substituting all of these values in, n is equal to the ln of 1 minus your present value, 72,000, times your equivalent interest rate, 0.0075, divided by your payments, which is 4,000, end bracket, divided by the negative ln of 1 plus 0.0075. Okay? Actually, sorry, I used the wrong interest rates here. See, again, it's an easy mistake for you to make. I used the periodic interest rates. Remember, you just saw me make the mistake on video, and I'm not taking it off the video, so you can see. I have to use the equivalent interest rate. The value I used was periodic, which is wrong. Okay? So replacing those, in the numerator, I have 72,000 times the equivalent interest rate, which is 0.02267. And in the denominator, it was the negative ln of 1 plus that equivalent interest rate, 0.02267. So this is one of the reasons I like to see your work. You just watched me make a mistake and fix it. Like I said, I'm not taking it off the video because those types of mistakes are easy to have happen. All right. So continuing on with this, okay, if you simplify this, you should get n is equal to the ln of 0.59194 divided by the negative ln of 1.02267. Now, if you calculate those out to the next step, you should get the numerator of negative 0.52435 divided by negative 0.022417. Okay? If you solve for that in your calculator, you'll get a value of n of 23.4-ish, which means about 24 payments. Okay? So our last example for this lesson, let's hope I don't make the same mistake I just did in the last example and make a mistake, but we'll see how it goes. Janet received a $12,000 bonus. She invested the money in an annuity that provides semi-annual payments of $1,600. If interest is 3% per annum compounded quarterly, how many payments will Janet receive before the money runs out? So again, she received a bonus and invested it. So you know that that's the amount of money she has now. So that is the present value. Okay, the other thing that you're noticing is how many payments. So you know you're looking for the value of n. Okay, and since it's present value, you start with the formula. N is equal to the ln of 1 minus the present value times the equivalent interest rate P divided by your payment, and bracket, divided by the negative ln of 1 plus the equivalent interest rate P. So now again, what do we know? Our present value we know is 12,000. And our payments that she's receiving are 1,600. Both those were provided in the question. Your nominal interest rate, J, is 3%, which is 3 divided by 100, removing the percentage sign, or 0.03. M, your number of interest compounding periods. Okay, interest is compounded quarterly. So the value of M is 4. So your periodic interest rate I, which is J divided by M, is equal to 0.03 divided by 4, which is equal to 0.0075. Next, just like we have, which calculates C, it's the number of interest periods divided by the number of payment periods per year. So interest is quarterly, so it's 4, and she's getting semi-annual payments, which means her number payment periods per year is 2. So her value of C is 2. Now we can calculate our equivalent interest rate P. It's 1 plus the periodic interest rate to the exponent C minus 1, which is 1 plus 0.0075 to the exponent 2 minus 1. And if you calculate that out, you get a value of P of 0.015056. Again, I'm keeping a lot of these decimals, and that's because these small numbers, when you combine them all, it does make a slight difference in what you might get for your final answer. Again, I can see all of your work during the test, so it makes it easier to assess that, but I'm keeping more decimal places than you might, which is okay. Just know that your answer might be a little skewed. So substituting all of these values, n is equal to the ln of 1 minus our present value, 12,000, times our equivalent interest rate, 0.015056, divided by our payments, which were 1,600. And that's all divided by the negative ln of 1 plus that equivalent interest rate, 0.015056. Okay? Again, simplifying this, you should get that n is equal to the ln of 0.88708 divided by the negative ln of 1.015056. Calculating those out, you'll get negative 0.11982 divided by negative 0.014944. Okay? Seems like a lot of numbers, but I just want to give you more ability to diagnose any issues you might have. So, finishing that, your value of n comes out to 8. So in other words, 8 payments. Okay? So that was all I had. This is the last lesson for unit number 3. So as you'll see on our unit 3 test, it covers lessons 3.1 and 3.3. 3.2 is the lesson using Microsoft Excel. My testing for you on that is covered in the assignment. Okay, so for your test, you need to know lessons 3.1 and 3.3. Again, if you have any problems, just send me an email. I'll be happy to answer them. I wasn't receiving emails for a couple days, but it looks like everything's been fixed at the college. So thanks, everybody.